So a basis for a vector space V is a linearly independent or dependent? Independent set that what V spans? Yeah. Linearly independent set that spans the entire vector space. True or false? This set is a basis for R3. It's false. Why is it false? It's linearly dependent. When you have more vectors than there are entries in the vectors, remember that that was an automatic, they're dependent. So this one is a false. We'll say because the set is linearly dependent. It doesn't satisfy both of these things. True or false, the pivot columns of a matrix A form a basis for the column space of A. That's true. Okay, so before I start today's lesson, I just want to remind you, I'm sure you are all aware, that test 2 is Monday. So today's lesson, I tried to shorten as much as I could. It's just a demo, and then the group activity time, you can work on a study guide that I've prepared for you. So let's look through the reading notes. So remember, this is something that we've known for quite a while. A set or a list of vectors is linearly dependent if and only if some vector in the list can be written as a linear combination of the vectors before it. Free variable, yeah, would be linearly dependent, correct. Okay, so a set of vectors forms a basis for a vector set if the set is linearly independent and if the vectors span the vector space. So what that means is that the span of the vectors has to equal the entire vector space, which means that linear combinations of the vectors given can generate any element of the vector space. So in shorthand, a basis is a spanning set that's as small as possible. Doesn't have any extra vectors in it. The standard basis for Rn is the columns of the n by n identity matrix. Standard basis is like a vocab word. It's called the standard basis, the columns of the identity matrix. The columns of an m by n matrix are linearly independent if there's a pivot in every column. Already knew that, right? And the columns of a matrix span Rm if there's a pivot in every row. So if you're going to be both linearly independent and span Rm, you have to have a pivot in every column and a pivot in every row, which means the matrix has to be square, yep, and invertible, yeah. Okay, so the spanning set theorem says that if S is a set of vectors that spans a vector space, so you know that the set of vectors can generate the whole vector space, you can remove any vector that's a linear combination of the others and still have a spanning set. Okay, so you can shrink that set down until it's linearly independent. If you go past that, it no longer will span the set. But you can take out any linear combination vector. Yeah, you can, well, you're not turning a dependent set into an independent set. You are removing the vectors that make it dependent. Yeah, remove the vectors that make the set dependent, and you will still have a spanning set. So if you're trying to create a basis, if you have a spanning set, remove the vectors that make that set dependent, and you'll be left with a basis. So that means that some subset of a spanning set is a basis. Any spanning set, if you take some subset of it, you get a basis. Sometimes the whole thing is the subset. Okay, so to find a basis for the null space of a matrix, we already know how to find a spanning set for the null space. That's what we did last class. We augment it with zeros, row reduce, put it in parametric vector form, and then those vectors that come out in parametric vector form, they form a spanning set. they also are always linearly independent. So you can just do the exact same procedure we learned last class, and you'll end up with a basis. To find a basis for the column space of a matrix A, you row reduce it to figure out where the pivot columns are, and then take those columns from the original matrix, not the reduced matrix. You're going to go back to the original and take the pivot columns. Excuse me. All right, so let's do a quick demo. So I've got two vectors here, 1, -2, 3, and -2, 7, -9. Does the set of those two vectors form a basis for R3? So are they linearly independent? Yeah. Anytime you have a set of two vectors, you can tell if they're linearly independent by checking to see if one is a multiple of the other, right? That's not the case here. So they are linearly independent. So that's half the definition of a basis, right? Do they span R3? Yeah, how can you tell if they span R3? So if you take linear combinations of those two vectors, you're going to get another vector in R3, but can you get any vector in R3? No. Like, how can you figure that out? That's true. In order to get a set that spans R3, you need at least 3 vectors because of what we said back here, right? If we want the columns of the matrix to span Rm, there has to be a pivot in every row and a pivot in every column to make it linearly independent. So it would have to be a square matrix, right? If I look at this as a matrix where these vectors are my columns, a pivot in every column tells me that it's linearly independent, and a pivot in every row will tell me if this thing spans R3. Yeah, so if there are more rows than columns, you can't have a pivot in every row, right? So there's no way, not a pivot in every row implies that this does not span R3. So it is not a basis for R3. Okay, does it form a basis for R2? Think carefully. Yeah, it would have to be square to form a basis. But when I take linear combinations of these two vectors, what kind of vectors do I get? 3-dimensional vectors. You can't span R2 with 3-dimensional vectors. You would need 2-dimensional vectors. So this is definitely a no, right? It doesn't even create a subspace of R2. It's different dimension. It's okay so far? All right, so let's try to find a basis for the set H that looks like a real number, 0. 3 entry vectors that are just number, 0. And those two numbers can be different. 1, 0, 0, and 0, 1, 0. Okay, so this is our proposed set that would be a basis for H. Are those two vectors linearly independent? Yes, they are. Right, one is not a multiple of the other. Is the span of those two vectors equal to the set H? Yes, linear combinations of those two vectors create vectors that look like some number, 0. So this is a basis. It's a linearly independent set. And the span of the set which we've been practicing coming up with vectors that span a set described like this. Now all you have to do is check to make sure that those vectors are linearly independent, and you've got a basis. So my two conditions are met, we have a basis. So basis is like the building blocks of a set, like the smallest set of vectors you can use to generate the entire set. Okay, so here's a matrix A. I want to find a basis for the null space of A. So last class we talked about how to find a spanning set for the null space of A. We want to like describe all the elements in the null space. And the null space is the set of all vectors that get sent to 0 by matrix multiplication. So I have to augment this thing with zeros. Right, because I'm trying to figure out what vectors do I multiply by A to get the 0 vector. That's the definition of the null space. So I augment this with zeros and I row reduce. I'll just use my calculator. This is going to be 3 by 5. And of course, I can't see the whole thing in my screen. Yeah. Cool. Thank you. Okay, so I have 1, 0, 0, 0, 1, 0, 6, 2.5, 0, 5, 1.5, 0, 0, 0, 0. Okay, so if I want to write the solution set as the span of some vectors, I have to figure out what are my free variables and what are my pivots. Good. So I need to rewrite x1 and x2 in terms of the free variables. So I'll say x1 is negative 6x3 minus 5x4, and x2 is negative 2.5 x3 minus 1.5 x4, and that's it, right? So then I have two free variables, x3 and x4. So I want to write this general solution set using my free variables as weights on a set of vectors. So a typical solution, x1, x2, x3, x4, is going to look like, well, x1 is negative 6x3 minus 5x4, and x2 is negative 2.5 x3 minus 1.5 x4. x3 is free, so I'll just put x3, and x4 is free. So that's what a typical solution looks like. And now I just want to break this out where I use my free variables as weights. So I'm going to have an x3 times something and an x4 times something. Okay, so x1, my first entry here, there's a negative 6 on the x3. So for my row reduced echelon form, right, this says that x1 plus 6x3 plus 5x4 equals 0. And then I moved the 6 and the 5 over. All right, and then in the x2 entry, the coefficient on x3 is a negative 2.5. In the x3 entry, the coefficient on x3 is a 1. And in the x4 entry, there's no x3, so I put a 0. And then my x4 vector, I'm going to have negative 5, negative 1.5, 0, and 1. Those two vectors that I just came up with by doing parametric vector form, the span of those two vectors is the entire null space, because that's what that says. Linear combinations of those two vectors make the null space. Are those two vectors linearly independent? Yes. And they will always be, because by the nature of using the, like, sort of removing the free variables, you're removing the linear dependence, right? So those will always come out as linearly independent, and those two vectors will form a basis for your vector set. So my basis is the set of these two vectors, because they span the null space and they're linearly independent. So this is exactly what we did last class. Last class we found spanning sets for the null space. Now that spanning set, we're just renaming it a basis, because it will automatically be linearly independent using this procedure. All right, how about the column space? If you want to find the column space of a matrix, the first and the last vector, is that always the case, or how'd you come up with that? Ah, the middle two are linear combinations of each other. I don't think so, because 4 times negative 2 is negative 2. Negative 6 times negative 2 would be positive 3. They look like they tricked you. Yeah, so if you want to figure out which vectors are linear combinations of the others, you can row reduce, and the pivots form a linearly independent set, because any column that doesn't have a pivot can be written as a linear combination of the pivots. So we're just going to row reduce it, which we already did, right, over here. So my pivot columns were 1 and 2. My pivot columns were 1 and 2, so I take columns 1 and 2 of the original matrix, not the row-reduced matrix. So those two vectors form a basis. Pivot columns of A. One and 2 form a basis, a linearly independent set that spans the column space. So in this case, we've got negative 2, 2, negative 3. And 4, negative 6, 8.